This video is to show you how to figure out if a molecule is polar or nonpolar. So the first thing that you're going to need to know is you're going to need to know the geometry of the molecule, because if the geometry is bent, pretty much it's always polar. So if you draw the structure and you know that the geometry is bent, you know that it's always polar. If it's trigonal pyramidal, it's also always polar. But you need to draw them. Now linear, it depends. And so in a minute I'm going to show you how you would have to draw this and use the dipoles to determine if the molecule is polar or not. All right, and then, oops, I don't want that. Let's see, so then, let's see, let's skip ahead here. Also, if it's trigonal planar, you have to draw it. And if it's tetrahedral, you have to draw it. So I'll come back to those in a second. So let's say we had a problem like this. It says draw the Lewis structure and determine the polarity of this pH3. So the first thing that you would do is you would draw pH3. So you would go P, and I'm just going to kind of take a few shortcuts on the Lewis structures because I know how to do them. But you would have to make sure you know what you're doing. And so this is what you would get with pH3. And if you look at pH3, if you can figure out the geometry, the electrons want to be as far apart as possible. So this geometry is trigonal pyramidal. And anything that's trigonal pyramidal, it's always polar. So just because you know that it's trigonal pyramidal, you can say that it is polar, abbreviated with a capital P. All right? And so let's try another one here. Draw the Lewis structure to determine the polarity of SO2. So we'll say S is the central atom, and then it's going to double bond an oxygen there, and then it's going to double bond another oxygen here, and there'll be a lone pair here. Oops, I screwed something up. This actually, if I remember right, should be a single bond there. Oops, wrong thing. And so then what we end up getting is this. Okay, now whenever you have three things and there's a lone pair on the central atom, that gives your geometry as being bent. And bent molecules are always, always polar. So you could say SO2 is a polar molecule. All right, now let's go back here to this one here. Okay, so bent, they're always polar. Trigonal pyramidal, they're always polar. You just know that. That makes it easier. Now, when it's a linear, it's a little bit more difficult. So let's say we had HCN, and let's say you drew the Lewis structure and you came up with this structure right here, which is the right one, or the most plausible one. And so then what you could do is you could look up the electronegativities, and you'd find that carbon is slightly more electronegative than hydrogen, and nitrogen is more electronegative than carbon. And so what you would have, if you had this molecule, let's say, the electrons would not be evenly distributed. There would be more electrons on this side of the molecule versus this side over here. The electron density is concentrated to the nitrogen side because nitrogen is more electronegative. It's going to attract electrons better to itself than these other two. And carbon is slightly more electronegative than hydrogen, so it would attract it just a little bit more over here. So this side of your molecule over here would be slightly negative, and this side over here would be slightly positive. And because this molecule has a negative and positive end, it would be classified as a polar molecule, a molecule having oppositely charged ends. All right, let's look at CO2. So if you drew CO2, you'd get C double bond O here, C double bond O here. And you would say, well, oxygen is more electronegative than carbon, so that oxygen is going to pull carbon's electrons towards it that way. But this oxygen is equally as electronegative as the oxygen on the other end, and so it's going to pull that way. And what you would notice is that the pull from each oxygen would be equal but opposite in direction. Now, this is a linear molecules, but the dipoles would cancel each other out. So this is an example of a linear molecule where the dipoles cancel each other out. You couldn't put a negative or positive on either side. So this molecule over here would be classified as nonpolar. One kind of easy way maybe to figure it out sometimes is, let's say you cut it right down the middle. If you cut it right down the middle, is it the same on the right as on the left? And if the answer is no, then it's most likely going to be polar. If you cut this one right down the middle and it's pretty much the same on both sides, it's going to be nonpolar. That's one way to look at it. All right, let's try another one. We already did those two. Okay, trigonal planar. Okay, BF3, so you get boron trifluoride. Now, boron is a violator of the octet rule. It only forms 3 bonds. It doesn't have a full octet. All right, so this is the Lewis structure that you would get for boron trifluoride, and you would notice that there are 3 domains surrounding one middle atom, so that gives you the trigonal planar geometry. Now, here's how, let's take a look at that one. Let's do this next one down here. So we have BHF2. So it's going to be about the same, except there's a hydrogen in place of the fluorine. And so then you could draw these here. Once again, boron's a violator of the octet rule. That's supposed to be 2 electrons there. All right, now, anyway, if you look at these 2 molecules here, to see, okay, so this fluoride would pull this way, this fluoride would pull this way, and this fluoride would pull this way. If you added up all of these dipoles, they would all cancel each other out. And if you did the same thing down here, because hydrogen is not near as electronegative as a fluorine, the dipoles wouldn't cancel each other out. So kind of an easy way with a trigonal planar, if all 3 things are the same atom, it is a nonpolar molecule. If all 3 things surrounding the middle one are not the same, it's most likely going to be polar. That's kind of an easy way to do it. All right? Okay, let's look at one other example. Tetrahedral. Okay, it's going to be kind of the same as trigonal planar. So you draw the Lewis structure. So let me draw both of these right here. And so then we got this one, which will be okay, so I think I got those done. Okay, so now with tetrahedral, you just look for identical bond polarities, or the easy way is just to look at the molecules. If all 4 things surrounding the central atom are identical, that molecule will be nonpolar. If all 4 things surrounding the middle atom are not identical, it's most likely going to be polar. So you're just looking at that. That's kind of the easy way to do it. Okay, to review a little bit. Okay, bent molecules are always polar, like this one right here. If it's bent, it's always polar. Okay, if it's trigonal pyramidal, it's always polar. Okay, the trouble comes when you get linear molecules. Okay, when you have a linear one, if the dipoles are not equal and opposite in direction, the bond dipoles, then it's going to be polar. But if the bond dipoles are equal but in opposite direction, it will be nonpolar. All right. Trigonal planar. Just look at the 3 things surrounding the central atom. If they're all identical, nonpolar. If they're not all identical, polar. And the same thing for tetrahedral. Look at the 4 things surrounding the central atom. If they're all 4 the same, nonpolar. If they're not all 4 the same, polar. Okay, I hope that gives you some idea how to tell a polar molecule from a polar molecule, or a polar from a nonpolar. Okay, so I'm